All right, folks, now we're going to talk about light and electrons. What's going on with those electrons? When electrons absorb energy, they go up. They go up in energy level. They go further from the nucleus. You can put this many ways. They go to a higher energy level. Energy level. Okay, so if I've got my nucleus and I've got an electron around it, there are other shells out here like a 2s and a 3s and a 4s and a 5s, etc. And that electron that's here, when it goes up a level or it goes up 2 levels or 3 or 4, whatever, it's absorbing energy. And then it eventually falls back down. And when it falls back down, it releases energy. And when it releases energy in the form of light. So we will see something. Again, remember the fireworks example that we talked about in the podcast. That's a real good example of electrons absorbing energy from when the thing blows up and all that heat. And then as the atoms move further from the center and they cool off, they are giving back light. All right. If an electron absorbs a certain amount of energy, it must eventually, and what it must do is give it all back. All of it has to go back. Right? The further the electron drops, the more energy that is released, and hence the greater the frequency of light emitted, and hence the shorter wavelength of light emitted. Remember that your frequency and your wavelength are inversely proportional. So when one goes up, the other goes down. Okay. In your own words, describe a quantum of energy. Well, it is the amount of energy needed when that electron goes shooting up to the outer level from the inner level. That's a quantum of energy. That's how much energy it used. And when it comes back down, that's also a quantum of energy right there. And that's a second quantum of energy, not necessarily the same quantum of energy that it takes, that it gives off when it comes back down. So it can actually release this frequency of light and then that frequency of light as two separate events. In your own words, describe the energy of the photon of light in terms of quantas of energy. Well, again, the photon of light that is released has a certain amount of energy to it. And it's quantas of energy. It's chunks of energy. Okay, and it has to, we said it has to be a certain chunk. Okay, and it has to be a certain amount. And it can't vary. It always has to be that amount. In the fireworks example, as the atom cools down, what happens to the electron? And what effect does it have on the surrounding? Well, what happens to the electron as the electron cools down? We have our atom. Now we have this electron that's out here somewhere. Right? Now an example of this atom is the electron could fall all the way down here. And when it does, it gives off a certain amount of light. Now if we have an identical atom over here, and we have that electron that's way up here, it might only fall part way down. And then a moment later, it'll fall the rest of the way. Well, this one gives off one frequency of light. Right? Because it fell a long way, it is a higher frequency of light. Now this one fell 2 levels, so it looks like it's falling a significant distance and giving off a pretty high frequency, but not as much as the one on the left. And when that electron falls the rest of the way, it's not falling very far, so it's giving away a lower frequency. So potentially this could be violet, and this could be something in the middle like a green, and then this could be something in the red range. Or potentially this could even be in the infrared range so that we couldn't see it. Or this one could be in the ultraviolet range so we couldn't see it. So it's potential that we couldn't see any of these because they are all outside of our visible spectrum. Now Bohr researched the hydrogen atom, right? And he did that because it was simple. Only had one electron. So when electrons fall and the atom emits light, are all the wavelengths of light emitted visible? And we just explained that back in number 7, where if it falls a far enough distance, it's going to give off enough energy that this thing will be in the ultraviolet range. and it will not be visible. Whereas if it only falls a really small distance, it might potentially be in the infrared range and not give off enough light that we could see. Okay? And describe why all atoms have a unique special fingerprint. Well, the easiest thing to do is look at hydrogen, which has 1 proton in the middle, and then look at helium, which has 2 protons in the middle. Well, these are both positively charged, and this is only 1 positive. So all of our electrons for hydrogen and helium sit in the first energy level, right? Now, the electrons on the right are held in tighter because, if you remember, this is a smaller atom, and it's held in tighter because of the 2 positive forces pulling on the inside. Okay? So the one on the right is really smaller. So if one of these electrons goes from the first level to the second level, versus this electron going from the first level to the second level, it's easier to move this one, because it's further away from the nucleus, than it is to move this one. So since the one on the left is easier, that means it requires less energy. Hence, when the electron falls back, it only gives less energy, and the one on the right would give more. Now that's a simplistic view of the world. We're only talking about 2 elements. But when you look at all of the elements that are out there, they all have these characteristics. Some, it's easier to take the electron away. Some, it's harder. So that answers the question of why they're all unique. Because in every case, you have a different number of protons in the middle, and the electrons are jumping from different levels. All right, that's it. If you have questions, ask me in class. I'll see you there. Have a good one. Bye-bye.